Okay. Um, let's start this one with a little bit of acid-base nomenclature. What I like about this chapter is that it tends to be a review of things that we've done before. So I know it seems daunting with the length of the videos, but really it's a matter of applying stuff that we've already done before. And in a normal school year, it would be a good preparation for the final, or if you're taking this as a summer class online, then it is a good review for the final. But we're going to start with some nomenclature, and this is all stuff that we did back at the beginning of the course. So acid-base nomenclature. All right, we said that there were two types of acids. There are what we call binary acids and ternary acids, or what they sometimes call a subgroup of ternary acids is something called oxoacids. Okay, binary acids are acids that are formed, and when you look at their formula, you'll see that there's an H plus, and there's also some sort of negative charged non-metal particle. So a good example of a binary acid, okay, would be hydrochloric acid. All right, so if we have HCl, the H provides the positive, and the chlorine provides the negative. And if it's a binary acid, we said we're going to use the term hydro. Hydro, whatever, ic, acid. So binary doesn't mean two atoms in the formula. It means two different atoms in the formula. So in this example, it's hydrochloric acid. But in this example, this would be hydrosulfuric acid. Hydro whatever ic acid. And again, it's binary because there's two different elements. There's hydrogen, which provides the positive charge, in this case 2 hydrogens, and then there's the sulfur, which provides the negative 2 charge. So if I'm naming HF, first of all, I'm going to notice that this is going to be an acid nomenclature because I have an H that provides the positive charge. The fluorine's group 17, so it's a negative 1. And that hydrogen is bonded to a non-metal negatively charged particle. So I'm going to use the term hydrofluor. Instead of fluorine, we cut it down to fluor and then add ic. So hydrofluoric acid. Put a bunch of those on the test, right? Because that's easy. It's a review of what we've done before. Now, ternary acids, the hydrogen provides the positive, but the negatively charged particle comes from a polyatomic group. So we got to go back to those groups that I asked you to memorize, like SO4 2- is sulfate, C3O 2- is carbonate, and NO3 negative nitrate. Let's do phosphate. Chlorate. And then we had acetate. And the other two that we were dealing with was ammonium. Remember I said there were 8 polyatomic ions. I wanted you to know. Ammonium, but that's not a part of a ternary acid. That is an acid, but it's not going to be ternary acid. And we also had OH- hydroxide that I asked you to memorize. Okay, so whenever it comes from a polyatomic ion, the number of hydrogens in the formula, you use the amount that's needed to balance the charge. So if we were to add 2 hydrogens to sulfate, we would get H2SO4. And the naming is you take the name of the group, get rid of the ATE, and substitute in ic, so this becomes sulfuric acid. If we were to write the formula for nitric acid, we would use H plus for acid, and then NO3- for nitrate, and it only takes 1 hydrogen to balance the charge, so our formula would be HNO3. All right, so again, sulfuric acid. Saw that on a test. I want to recognize that that's an acid nomenclature because it's got the H plus in it, and the polyatomic group is sulfate, right? So I'm going to change the name from sulfate to sulfuric. So again, the simplest nomenclature we learned at the beginning of the year with acids was if it's binary, make it hydro whatever ic, and the whatever is the non-metal. So the first one is hydrosulfuric. HBr would be hydrobromic, and yes, you do have to include the word acid, because if HBr was a gas, instead of dissolved in a water solution, we would call it hydrogen bromide. And then HI would be hydro, iodine becomes iodic, hydroiodic acid. If it comes from a polyatomic group, then we take a look at the group from the chart we memorized, and we change the ending from ATE to ic. So if it's got, if it got phosphate, then we're going to call this phosphoric. Nitric for nitrate. And then I'm going to pause while you do the last one. Okay, we're back. This comes from chlorate, so this is chloric acid. Okay. Now the oxoacids. They call them oxoacids because they come from polyatomic groups, and they have oxygen in their formula. Now they follow a pattern. The ones I asked you to remember: NO3, carbonate, sulfate, phosphate. Notice they're all ending in the ending ATE, 8, chlorate. And we said that whenever we turn these into acids, we use the term ic in the nomenclature. So if we add 2 hydrogens to carbonate, then instead of carbonate, this becomes carbonic acid. Okay, so if you memorize this chart, then you can derive the names of all the other acids by comparing their formula to the formula you know. Okay, we said that if we did carbonic acid, H2CO3, it comes from carbonate. However, carbonous acid comes from what's called carbonate. So if you take the formula for the ones you memorized and you subtract 1 oxygen, instead of using the term ic in the name, we're going to use the term us. So if it comes from CO2 2 minus, well, that looks almost exactly like CO3 2 minus, except for it's got 1 less oxygen. So the acid that comes from that, H2CO2, this would be called, instead of carbonic, this would be called carbonous acid. Now, if you subtract 2 oxygens from the formula, then instead of the term us, you're going to put a hypo at the beginning because it comes from the hypo whatever ion, and we're going to change the ending to us. So instead of us, you drop 2 oxygens and it becomes hypo-us. So let's say we had the acid that comes from this ion, ClO minus. Well, ClO minus looks suspiciously like ClO3 minus, which is chlorate. So instead of chlorate, it comes from hypochlorite. And so instead of calling it chloric acid, we're going to call it hypochlorous acid. And then the 4th type of oxoacid is when you add 1 oxygen to the polyatomic group. Now, in Latin, these names, these stems, if you use the term ic, it means more. If you use the term us, it means less. So the ones that end in ic in their name have more oxygens in their formula, and those that end in us have less oxygens. So we already used ic for the column I had you memorize, but if you add one oxygen to that column, like ClO4 minus, again, it looks suspiciously like ClO3 minus, which is chlorate, but this is called perchlorate. So the name of the acid is going to be per whatever ic acid. So instead of chloric acid, we would call this perchloric acid. And that's an easy way, unless you're going to memorize all the oxoacids, that's an easy way to kind of derive their formulas. I didn't write the formula for hypochlorous acid, so I'm going to go back and do that. HClO. Okay, so we have per ic, us, and hypo-us, depending upon how the formulas compared to the ones that I asked you to memorize. So I had a dual purpose back then for having you memorize those formulas. It wasn't just about lab work, and it wasn't just about helping you through the nomenclature in the fall, but coming back to the spring, memorizing the terms for oxoacids are difficult. Another thing too, like if you have something like chlorate and you have another element in the same group like bromine, bromate would have the same structure as chlorate, except for we're going to substitute a bromine for a chlorine, so this becomes bromate. And if they gave you HBrO2 on a test, then the name of this acid, instead of bromate, it's going to be bromite. So instead of bromic acid, this would be bromous acid. It's actually not a difficult system once you've seen it. Now, as far as the organic acids, we're not going to do those at this level. Things like hexanoic acid or pentanoic acid. But if you remember back at the beginning of the year, hexanoic means 6 carbons in it, so it would be an organic acid with 6 carbons. As far as the bases, the only bases at this level are going to have OH minus in their formula, and they're very easy to name. We just name the metal and then end it with hydroxide. Doesn't matter how many hydroxides they are. So sodium hydroxide, NaOH, pretty easy, right? Sodium for the metal, hydroxide for the OH minus. But the second one is just called magnesium, not dihydroxide, just hydroxide. Now, there are organic bases, amines and amides, but we're not going to do them at this level. And you may recognize amine from the term amino, so having an NH2 group in it. From biology, amino acids. All right, reactions involving salts. There are 3 types of salts. There are salts that, when you dissolve them in water, do not change the pH of the water, the acid environment, which we call neutral salts, like when you put table salt in water. The NaCl particles do not change the pH. But if a particle can react with the H plus that's in the water or with the OH minus that's in the water, it will change the pH. So there are acidic salts and there are base salts, or what they call alkaline salts. However, we're only going to look at one type of salt, and we're going to call them anhydrides. Anhydride meaning without the water. So without the water, this is a salt that is waiting to become something else. So if we have an acid anhydride, it's a salt that when you add water creates an acid. Or there are salts, when you add water, create bases, and those would be called base anhydrides. So anhydride means, again, it's like an instant acid. Acid anhydrides waiting for water. As soon as you add the water, it becomes an acid. Now at the AP level, we'll talk about which particles do that, and more variety, and why they do that, and how much it affects the acid environment. Okay, so they called this type of reaction one of many different types of hydrolysis reactions where we're using water as a reactant, where a salt's reacting with the water and it's becoming an acid or a base. So for the acidic anhydride, they're not even going to use a salt. They're just going to use a covalent particle here. And the only ones that you have to know at the Chem 1 honors level is nonmetal oxides. Nonmetal oxides when reacted with water, become acids. So they would ask you to recognize an equation. For instance, carbon dioxide, we have to exhale carbon dioxide. Carbon dioxide, besides being toxic, is also acidic. It reacts with water, and we combine those formulas, and we get H2CO3. When we add up those formulas, then that's carbonic acid. So non-metal oxides mixed in water produce acids. Metal oxides mixed in water produce bases. Now, a lot of the antacid tablets have either aluminum oxide or magnesium oxide, some sort of oxide. May not be magnesium, I shouldn't have said that. I know aluminum's one of them. I don't actually remember which is the other salt, but it's a metal oxide that when it mixes with the water in your stomach produces a base. So if you have heartburn, too much acid in your stomach, then it will react with the acid because the metal oxide in the tablet will produce a base and the acid will neutralize the base. So again, they want you to know and recognize that reaction on a test. Any metal oxides, when you add water, they become metal hydroxide, so they become bases. So they ask you to write the equation for aluminum oxide plus water. Well, we know that metal oxides plus water produce metal hydroxide. So this is going to be aluminum hydroxide. Now, aluminum has a positive 3 charge. Hydroxide has a negative 1, so we need 3 hydroxides to balance out our charge. And then we have to go back and we have to balance the equation. So let's try a 2 in front of here. That takes care of my aluminum. And then we'll put a 3 in front of the water. Again, a salt is any ionic compound that doesn't produce H plus or OH minus. I actually went over that in the last video. Now, they're going to introduce the concept of strong acid, weak acid, strong base, weak base. Again, it doesn't have anything to do with safety. A weak acid can be just as dangerous as a strong acid. It also has nothing to do with pH. pH is not a measurement of acid-base strength. pH is a measurement of environment. For instance, if you take 1 drop of hydrochloric acid, which is a strong acid, and drop it into the ocean, it is not going to lower the ocean's pH to a 1 just because it's a strong acid. pH measures environment, not acid-base strength. Whereas you can have a lot of, or a highly concentrated version of a weak acid, and that can actually have a lower pH than a diluted version of a strong acid. So we use KEQ to measure acid-base strength. What determines the KEQ value is how many H plus ions it produces, how many ions. The more ions it produces, the larger the value. So if K approaches infinity, it means it produces 100% ions, H plus. We call it a strong acid, or 100% OH minus, strong base. Whereas a weak acid or weak base produces very few ions. And the example I used last time was vinegar, which has a Ka that's the same as ammonia's Kb. Ka is equilibria for an acid, Kb is equilibria for a base, and in both of these, only 1 out of about 180,000 particles actually produces the H plus or OH minus ions. Right, second type of reaction after hydrolysis is neutralization. When an acid reacts with a base, technically you could think of it this way: the acid destroys the base and converts the acid and base into salt and water particles. Remember, the driving force for this is the production of water molecules on our planet. Very strong driving force. So most neutralization reactions involve a single arrow. In fact, if you're writing the equations, use a single arrow anytime either the acid or the base is strong. But if both the acid and the base are weak, that's the only time we're going to use a double arrow. But either way, we approach the neutralization equation writing the same way. And that's what they want you to do on the test, is predict the products and balance the equation between an acid and a base. And we did something very similar to this earlier in the year. All right, so suppose we have a reaction between, and they want us to write the molecular version of the reaction. We're going to react HCl and we're going to react it with NaOH, and they want us to predict the products and balance the equation. Okay. We're going to split HCl up into H plus and Cl minus. Okay, we can do that. And then we're going to split the base up into its ions. We're not worried about balancing it yet. In this case it is, but we're not worried about doing that. And then we're going to switch the positions. The Na plus is going to go to the Cl minus, and that's going to produce our salt. And then the H plus is going to go to the OH minus, and that's going to create our water molecule. And then we just go back and balance the equation. So very simple. All acid-base reactions produce salt and water. Now, they don't all produce table salt, sodium chloride, but they'll produce some sort of salt, and of course the driving force is the production of the water molecule. All right, so try this one. We're going to react, and I'll let you know that this is single arrow, because both the potassium hydroxide and the hydrochloric acid are both strong electrolytes. Write the balanced equation for the reaction between HCl and potassium hydroxide. So I'll pause and come back. All right, I'm back. So we said we're going to take HCl, break it up into ions. H plus, chlorine group 17, so it's Cl minus. Potassium, group 1 metal, positive. OH minus, polyatomic group, we memorize it. We're going to switch ions. The H plus will go to the OH minus. The K plus will go to the Cl minus, and we get this reaction. HCl plus potassium hydroxide produces potassium chloride plus water molecules. All right, so I'm going to stop it here because it's been 22 minutes. And when we come back, I'm going to show you that that molecular equation we just wrote isn't appropriate, doesn't happen, because we're not dealing with molecules. We'll deal with what's called a net ionic equation. So thank you very much. See you on the next section.